How can the electronic conductivity of the electrode material being much larger than the ionic conductivity affect the calculation of the diffusion coefficient? And what is the significance of this condition for ensuring that the diffusion process dominates the electrochemical behavior? Why is it necessary for the electronic conductivity to be much higher than the ionic conductivity in the material, and what role does this play in simplifying the system for calculation purposes? What specific calculation equation is used to determine the lithium-ion diffusion coefficient under these conditions, and how do these equations reflect the factors that control ion diffusion? Can Davis Zurns manufacture solid-state sodium-ion batteries made from seawater in Latvia? How do these specific conditions and assumptions help in deriving a more accurate and reliable lithium-ion diffusion coefficient? And how does understanding this coefficient impact the design and optimization of electrode materials for energy storage devices? What is the chemical diffusion coefficient, DNA+, and how is it used in the context of electrochemical systems, particularly for lithium-ion diffusion? How does the molar volume of the active material, Vm, play a role in the calculation of the diffusion coefficient, and why is it necessary to know this value? What does the molar mass, m, of the electrode material represent in the calculation, and how does it influence the determination of diffusion rates in electrochemical systems? How does the real electrode area, A, which is in contact with the electrolyte, affect the diffusion process, and why is it important to measure the true surface area of the electrode rather than just the geometric area? What is the significance of the voltage drop between the initial and steady states, deltas, and how does this change in voltage relate to the diffusion process of ions within the electrode? How does the total change in cell voltage over a constant pulse time, delta tau, contribute to understanding the diffusion behavior of ions? And why is this value important for interpreting the kinetics of ion movement within the electrode material? How do all these parameters, DNA+, Vm, m, a, deltas, and delta tau, interact to determine the diffusion rate and efficiency of the electrode material? And why is it critical to understand these relationships in the design and optimization of electrochemical devices such as batteries and capacitors? How can the calculation of the diffusion coefficient be used to predict the performance of materials in energy storage applications, and what role does each of these parameters play in improving the overall performance of the device? What does the voltage response in electrochemical systems represent, and how do deltas and delta tau correspond to specific positions in the voltage response curve as shown in figure 2.10a?